Today's combustion engines operate at approximately a maximum thermal efficiency of 25%. The intent of our project is to try to improve that. The main part to improve that we're going to be focusing on is the camshaft. And since the beginning of combustion engines, they've all operated utilizing a camshaft to actuate the valves, the intake and exhaust timing. And they work by, essentially there's two lobes here, one for intake and one for exhaust. This is hooked up to the output shaft, and as it turns, it pushes a push rod which then actuates the valve or opens it and closes it. And the timing is dependent on the location of these lobes as it spins.
Instead of utilizing a camshaft, we've decided to implement a pneumatic system, something that gives us the ability to have a free valve style system where we can switch between a 2-stroke, 4-stroke, even a 6-stroke. By doing that, we have set up a timing system that uses an encoder that drives a digital style camshaft, something that replaces this. By doing this, we can now run water as a 6-stroke, we can run air, and by injecting it into a hot cylinder, it will expand to steam and then eventually add power, or at least recover some energy from waste heat in the traditional 4-stroke.
Right, so these are the pneumatic actuators that control the valve actuation. They are supplied 100 psi of compressed air through this solenoid manifold that controls their actuation. This is connected to a filter as well as a regulator connected to our small compressor.
So here's a quick demo of our valves actuating using the digital encoder position, and Peter will spin it.
On the front of the motor, we have a flywheel that is integrated for testing, as well as a reducer to slow the engine speed before it is fed into our encoder, which translates the mechanical motion of the motor into electronic data. Alright, on this side of the motor we have our induction coil that acts as a distributor for our spark. We also have a servo motor controlled by a potentiometer on this side to actuate the throttle. At this end of the cart we have our electronics enclosed in plexiglass, and to describe the function of these parts I will hand it over.
So this is the electronic setup that we have built. This is the encoder, which measures the position of the engine. See, I'm turning it and it's registering where the motor is. If you look down here, this is the Arduino control unit that monitors the engine position and fires off the actuators. And as you can see, this light here indicates top dead center on the first revolution of the motor. You go past it, it shuts off, meaning we're past it. This Arduino controls the servo for the throttle, and these relays are what fire off the actuators and the spark. You can see the lights show when the actuators are going off.
So as far as testing is concerned, the first test we'll be testing will be finding torque and horsepower. Using our Deproni brake dyno, we'll use a leather strap, a pulley, and a strain gauge. On this side of the pulley, an adjustable will tighten up on the strap and seize the drive shaft while it's spinning. At that point, we can find the power using the equation power equals traction force times velocity. So the second testing we should do is testing fuel consumption using the brake-specific fuel consumption. The brake-specific fuel consumption is a test using a high-speed camera, a specific amount of volume, and our power figures from our torque measurement. The fuel consumption figure will be the rate of fuel consumption over the power. This value will be used to calculate the 4-stroke efficiency, as you can see here. The efficiency is 1 over the fuel consumption value times our gasoline energy density. So building an engine in 6 months is not an easy task. Therefore, we ran into some issues. So the first open issue we faced was choosing between solenoids and actuators for our valve timing. Solenoids were a chosen design by many other groups, however, it failed because at 100% duty cycle, the solenoids cannot keep up. In our case, we chose actuators, as you can see here. they're much easier to deal with because all they depend on is our volume of air. At a higher volume, the actuators can keep up. Ideally, at 100% force and 100% speed, adding more volumes behind multiple regulators would completely eliminate the stabilization problem.